Hello. Okay. We will wait another 2 or 3 minutes and then start the meeting. Beforehand, we are looking for a note taker and JavaScript pro. If anyone want to volunteer, let me know. Anyone? If you are interested in taking a notes, could you raise your hand? Oh, sure. Thank you so much. I know. This is so silly. Okay. Okay, so shall we start? Before we start, we want to have a JavaScript run. If anybody want to volunteer, it's very easy. You just check the web Java room, and if someone want to raise a question, please speak up to the mic. That's all. Anyone can take it. If anybody interested, could you raise your hand? Okay, thank you. Thanks so much. Okay. So let's get started. So welcome. This is multi-pass TCP working group meeting. My name is Yoshi Nishida, one of the co-chair of the multi-pass TCP working group. And unfortunately, Phil cannot come to this meeting, but I think he might be in a remote. Okay. And we already got one note taker, thanks Stuart, and JavaScript. So before we start the meeting, I would like to keep one thing, remind you. When you speak up at the mic, please say your name before you speak something so that the note taker can track your name. And when you submit your draft, please include Mptcp in your draft name so that chairs can track the status of your draft. And finally, don't forget to write down your name on the blue sheet. Okay, this is user note well, so please keep this in your mind. So basically what you said in this meeting will be governed by this note well. Please remember this. And this is the agenda for today's meeting. At first, Chair will talk about working group status and so on. And after this, we have 3 presentations. The first one is consideration for Mptcp operation in 5G. And the presenter is Akbar. And then after this, Jing will talk about a productive approach to avoid performance degradation on Mptcp. And then after this, Brad will talk about SOX version 6. So for some reason, we have 3 presentations this time. So, but that means we have a certain amount of time for discussion if we want, and so which may be good. And so any comments or question on the agenda? Okay, moving on. So let's talk about the working group status. So we are trying to complete the BIS draft right now. And then in chair's understanding, there are several remaining items before we finalize the draft. Removing address identifier from MP Prior. This one has been proposed in the last meeting, and I think we got enough support for this one. And then this one is already incorporated into the BIS draft. So I think this is already done. And guideline about Mptcp and TFO interactions. For this one, we are waiting for the proposed text from the authors. So let's wait the text from the authors. And then once we got the text from the authors, we can review it, we can discuss it. And the next one is first close updates. So there are several discussions on the first close approach, which is slightly different version, what is written in the BIS draft. And right now there are several discussions. And then this morning, Olivier sent a new proposed text to the mailing list. So please read his mail and provide some comments, and then we can continue the discussion. And then I think Olivier is in remote. So if I don't recommend to do very detailed technical question right now, because we don't have a slide and then Olivier is remote. But if you have some clarification questions, maybe you can speak up right now. And okay. And then also reason code for Mptcp reset. This has been discussed in the last meeting. And I think we need to see proposal before we need to discuss whether this is going to go BIS draft or not. So I think the author should prepare proposal in order to proceed this one. So these are the items that chair think remaining items. And if there is other stuff that should be discussed in the BIS draft, please let us know. Otherwise, we will focus on this draft to finalize the BIS draft. So, any missing items? Do you have any opinions about it? Okay, seems to be good. And then the progress of BIS draft is really, getting delayed these days. So this is just a brief idea, but Phil and I are discussing about having interim meeting, let's say in January or February timeframe. And if people think this would be useful to accelerate the process of the finalizing BIS draft, yeah, Phil and I will happy to arrange the interim meeting. So if you have any opinions or suggestions, please let me know. Anything? Okay. So far there is no preference to having an interim meeting, at least in this room. Okay, moving on. And then there are several discussions about MP proxy activities these days. And currently we have 2 drafts. And one is SOX version 6 approach. This is purely application protocol. And then next proposal is Mptcp converter. This draft is more focusing on the Mptcp to align with our charter text. But the converter text has some kind of generic mechanism. And then because of this generic mechanism, we might apply this almost same architecture to other TCP extensions. And for example, we might be able to apply this technology into TCP Inc., which might be interesting use cases. So after think about this kind of possibility, working area director and Mptcp chair and the TCPM chair has several discussions, and then decide to have a small discussion in the TCPM working group on Thursday. So if things goes well, we are thinking about running adoption call on this draft on the TCPM working group mailing list. But still, we need to discuss it. So the main focus on the Thursday discussion in TCPM is to discuss the future direction of this draft. So if you are interested in some opinions about the future direction of this draft, whether this is only focus on MPTCP or it should have MPTCP should have more like a generic mechanism for any kind of transport extensions, please provide your feedback. Okay.
Cisco. I'm just curious as why this group is not taking up this work item.
Milia, want to say something?
Mia Kulevin. So the mechanism described in the document is actually generic to any kind of TCP option, might be most useful for MPTCP. However, given this is a generic mechanism, we want to see if there's interest in the TCPM working group. We go straight to for an adoption call. Unfortunately, the authors cannot be here to give a presentation. That would be much easier. However, we run an adoption call. If the adoption call fails, which means there's like no interest in that group, we can still bring it back to MPTCP, but that would automatically mean that it would be only focused on the MPTCP use case.
Right. So basically, we will discuss the future direction of the draft in TCPM. So we don't say, we are accommodate this draft in TCPM right now. We just try to discuss, figure out what people think. That's the motivation. And then, so as Milia said, the author is not in the venue. So the Thursday meeting is not a chance. It's not we are not focusing on detailed mechanism of this converter draft. We are just talking about discussing about the future direction of the draft. That's the purpose of the discussion in TCPM. Just I would like to make sure. Okay, then implementation news. So as you might notice, we got new Mptcp Linux kernel implementation The version number is 0.93, and it has been released November 2nd. And this release mainly focused on standardization work, stabilization work, bug fixes, and then catching up with upstream. So as a result, the current Mptcp Linux implementation is based on Linux kernel version 4.9. And then because of this, it allows user to utilize Mptcp with TCP PBR. And this might be related to the Jing's application today. And then also, they are also focusing on the catching up upstream. So their plan is next release will be based on version 4.14. So do some refactoring in order to catch up the upstream. That seems to be their plan. So any comments about implementation news? Or if you know other implementation news, please let us know. Okay. Okay, this is the end of the chair's right. Any comments from the chair's right? Any comment on chair's right? Okay. Then let's move on to the presentation. Akbar. Do you have this one?
Okay.
Hold on. Yes. Always missed. Always missed. Okay, good.
Okay. Thank you. I'm presenting on behalf of my co-author Debashish. He's the main author, but he had a conflict with another group. So we wrote this draft after the Prague meeting because we had asked a question when there was an Apple implementer who was describing the Apple implementation of Mptcp, and we had asked if the Apple implementation considered multiple IP addresses being possible for a given interface, specifically for cellular. And our understanding at that time is he said no, and he would be interested in knowing what use case that might occur in. So that's basically what we tried to document in this draft. So I think everyone here is of course the experts on Mptcp. So basically the basic idea though obviously is if you have multiple interfaces, meaning practically speaking Wi-Fi and cellular most of the time, it's trying to do bandwidth aggregation, redundancy, reliability across these different interfaces. But our understanding is that it assumes basically you have one IP address per Wi-Fi or per cellular, which is fine because that's I think the way it works today. But if you look into the 5G discussions in 3GPP, basically they're moving from the current, let's say, hierarchical or the model for mobility management that they have in 3GPP currently for 3G and 4G, is that the anchor point is usually the what they call a PGW, or the gateway in the network, and it's pretty far up in the network. So even if you have mobility going around at the radio access, the anchor only sees or only assigns one IP address per UE for what they call the PDU session, and the mobility is taken care of more or less at the radio access network, and your IP address doesn't really change because of that. But what's happening for 5G and 3GPP is they're moving to a more distributed and closer to the edge mobility model. And basically, what they're going to do is to support the make before break, essentially. The make before break mobility is they're going to allow multiple anchors to exist simultaneously for a given UE. And we gave the reference of the 3GPP document that describes this, so you can confirm for yourself if that's your same interpretation. But I think the text is pretty clear there. And basically what will happen is for the equivalent make before break in 5G, you'll now in certain cases have multiple IP addresses being assigned to the given UE. So from the interface, if we call the whole cellular network the interface, you might have multiple IP addresses coexisting for a given UE at a given point of time, basically to to keep it simple, to have a make before break with the mobility anchors pushed towards the edge. So anyways, 3GPP always has very specific terminology. So here, they have this branching point and PDU session and all this, which is basically taken directly from their I believe it's a TS, the 3GPP document that's referred there in the draft. And really, we just wanted to bring it up to the group. If this really does cause any, potential issue, I guess Mptcp will still work, because at the worst case, you'll have multiple IP addresses on a given interface. And you might think you have a backup, but you don't. You might think you're doing bandwidth aggregation, but you don't. But I guess the algorithms will still take care of it. But you'll get the lowest possible throughput, I guess, through that given interface. And you might have a problem if you try to fall back and the actual fallback IP address is also disappearing. So really, all we wanted to do is follow up on the question we had asked, because we're following what happens in 3GPP, and basically want to bring it up to the group, whether they also see an issue and whether there's anything to be done.
Cisco. So I'm just curious, like from the endpoint today, when you open Mptcp sessions, right? Would you pick the address based on an interface, or would you pick multiple IPs? Why would you take multiple IPs from the same interface? When you're doing link aggregation, you will do Wi-Fi and LTE link aggregation, or LTE and DSL link aggregation, or whatever, right? Whatever radios interfaces that you have. In each interface, even today on wireline, I can get an IPv4 address or multiple IPv6 addresses, right? That's there even fixed line today, right?
Well, so, sorry to interrupt, Sri. What I understood, from it was the Apple developer last time who spoke, and when we had the question and answer, he was saying that they did not assume it. That's what I understood. He said they did not assume on cellular you could have more than one IP address.
No, but even if cellular, let's say on a given cellular interface, there are multiple IPs. Let's assume that. But from a UE point of view, would it open two Mptcp subflows from the same interface?
This is the question.
Why would they do that?
The reason is they don't want to use it for bandwidth sharing or anything like that. This is specific use case where mobility happens. Like for existing 3G, 4G use cases where Wi-Fi and cellular IP addresses are there and two separate interfaces, that is not changing in 5G. What is changing in 5G is UPF mobility, what you described, where temporarily subflow has to be created and the old subflow has to be removed. There's no bandwidth sharing or aggregation at this point.
Yes, thank you. Could I get your name? Just
my name is Uma from Huawei. I have some questions actually.
Thank you.
Stuart Cheshire from Apple. I'm not the Apple engineer you were talking about, but he's one of my colleagues. You asked the question here about how Mptcp would have to change or whether it would work, and I would put it completely the other way around. The issue that our current code only uses a single address, I think it's a minor engineering detail. It's nothing fundamental. What is fundamental is if a mobile device changes addresses as it moves around, then multipath TCP allows it to maintain a connection by bringing up new subflows on the new addresses and dropping the old ones. So it's traditional TCP that's going to fall on its face and break here, which makes this a very compelling argument for more use of multipath TCP, I think.
Okay, I read the draft and I'm not understanding what is that you are saying.
Well,
You are proposing some solution, or we are
no,
raising-
we're not proposing a solution. We're basically just trying to identify the use case. And if there is anything, or if maybe as Stuart is saying, there's nothing, it just makes everything better, that's fine too. So we're just trying to follow up on trying to understand how the system will work in 5G.
Okay, there was a discussion like few years back for the UPF mobility exact, the case you documented here, where 23.5.0.501 documented the branch point and UPF. There were discussion that they wanted to do the mobility to the UE, that is not anchor point mobility, like the existing 3GPP. They wanted to do the MPTCP all the way for the mobility management, but that was not done. So MPTCP only used for 3GPP and non-3GPP access, and the regular anchor point mobility is still there in the 3GPP. There is no change there, but I have lot of comments actually in this thing where you can document this just for the purpose of for future references where this can be used. I'll take it offline with you.
Yeah, or yeah, we can talk offline, and maybe we can talk on the email list too, just to make sure that everyone gets their input.
Mark Townsley from Cisco. I'm going to channel some of the people I'm working with, some of his colleagues, and some over at Google working on the Android platform. I think it's RFC 7934 that details all the reasons why you might have more than one IPv6 address on a given interface. It's not just in the 5G case. It's a general thing. Most hosts today on most interfaces can have multiple v6 addresses from multiple prefixes active at any given time. They may or may not result using different source addresses on a given interface to the same destination, could end up in a multipath situation. And Mptcp just should assume that addresses that are available are up for grabs for it to utilize, and not read too much into whether or not they're sitting on the same interface or not.
Okay. And what was the RFC you mentioned again, please?
7934, I think, is that right? It's co-authored by Vint Cerf, Lorenzo Khalidi, and David Skenazi. Okay.
Okay, thank you.
Maybe a follow-up question, Sri Gandaveli again. So are you hinting at essentially now that I understand what you're trying to say?
Sorry.
Okay.
So you want to hint the peer that both of these IPs, IP1 and IP2, belong to the same interface? Is that what you're alluding to? Is that the goal?
Well, basically, the reason we were interested in this is because we have colleagues from our company that go to 3GPP, and I don't think it was formally discussed there, but there was some discussion about since the model for 5G is changing apparently from what 3GPP does for 4G and 3G, was there going to be any impacts on the IP applications, TCP, etc.? So that's how we were originally interested in the problem, and that's why we had asked the question in the last IETF meeting, Mptcp meeting, and so basically that was our motivation. We don't have a particular solution or a particular suggestion that we had. We just wanted to understand how the system will work.
Okay, I'm not 100% sure this is an issue, but I'll try to understand. Thanks.
Okay, thank you.
Hi, Dave Allen from Ericsson. Yeah, I'm not sure this would end up being an Mptcp issue. Simply as my understanding of 5G, which I will admit is limited, is I'm either going to have, in the scenario where I have multiple anchor points in the network, I'm either going to have a separate PDU session, or there is the notion that explicit flows will be identified and broken out. From the point of view of proxies, that's probably addressable with policy, which is simply if I'm going to have a flow that I'm going to break out early, I would not send it to, I would identify that traffic as something I would not want to send to another proxy. As far as end systems are concerned, where, for example, Stuart's case, what's going to go to Apple probably isn't going to get broken out early. So it's not obvious to me you would actually have an issue there. A lot of the early breakout scenarios are concerned with non-mobility and Internet of Things. So
yeah, for this, I'm sorry, I don't know if I closed it by. For the within the network, okay, I'm not sure where it's going. They have the branching points. If you follow the 3GPP, the latest TSs, I guess, they have this common, well, they call this a branching point. So my understanding is basically that's the thing in the network that's going to collect from the multiple anchors, and they're going to put it all together either on the downlink or the uplink and give it one face to the mobile. So that's my understanding how 3GPP is approaching it. And the other thing is, this was what our 3GPP people asked, these specs are still not finalized. So they wanted to know if there was any feedback we could give to the 3GPP side, if there was going to be any problems.
Okay, you're talking about 23502 or?
That, I think, I don't remember the number. I think that's what we reference, yes.
Yeah, okay.
Actually, you're showing the branching point solution in 501 because of the fact that you showed that means that they are not considering for UPF mobility, they're not considering Mptcp. That's one thing you have to bear it in mind. If it is wrong, tell me if that is wrong.
Can you just expand that, please?
Because of the fact that they are using branching point and two UPFs, that means they have a network solution for the UPF mobility. They are not going to come to Mptcp for that solution. So Mptcp today they are using for Wi-Fi to cellular, and that is being used. And there was discussions for using UPF mobility, but because of the fact that you are showing the branching point and two UPFs, they have a network solution.
Okay. Okay, thank you.
One comment. Fabian previously proposed maybe some useful proposal, maybe related to your approach. So what Fabian proposed is when you Mptcp endpoint announce the IP address, he basically proposed to put some kind of communication ID. Let's say if I have 4 IP addresses, and then A and B has the same interface, I can set the same communication ID to the address, so that when you advertise address, you can know A and B are belong to the same interface, or C and D and the different interface, so that you can have some strategy to how you set up the subflow. That's kind of the approach he's mentioning. Is it related to your proposal? Maybe you can utilize it?
Yeah, I didn't have a proposal, but definitely I look at this. This is it was an old draft, you're saying?
It's expired, so I will send a pointer to you later.
Okay, that would be appreciated. Thank you.
Okay, but another question is, Mptcp is a transport layer protocol. So how Mptcp can know which address belong to which interface?
But I thought that multiple people implied that they would know that.
Okay. But you don't, so there is no standard mechanism in 5G, basically.
Well, in 5G, I guess you'll know over the cellular that you're getting multiple
How
IP
transport
addresses.
layer know?
The cellular interface will know how it,
Okay,
I guess it's not mandated that it has to share it, but I guess the implementation overall, the UE or the laptop or whatever is going to have that information available to it.
Okay.
Okay, thank you very much. And I'll follow up with the people who gave the comments. Thank you very much.
Okay, next. Thank you. Okay. Jink? You can use this. Yep. Yeah, ready.
Hello, everyone. Today, I'm going to present my draft, which is a proactive approach and to avoid the performance degradation of the Mptcp. So my name is Jin Zuo, and this is a joint work with my colleagues from Huawei. And first, let's see the Mptcp employment on the high-speed rails And here we utilize 2 LTE for the data transmissions. We found that there is a lot of handoffs. However, the handoff happens at different time because the base station provided by different operators, they are located in the different place. So the throughput for the different LTE, they happens at different time. Okay, we have spent 6 months and to do the experiments and to see how the Mptcp performed. And here we travel around more than 66,000 kilometers around China. You can see the high-speed railway map on the up right corner of this slide. And the highest speed of the rail can achieve more than 300 kilometers per hour. And we use UC, which is aggregation efficiency, and to see how the Mptcp perform. And this aggregation efficiency is aggregated throughput divided by the throughput of the best path. And when the UC is less than 1, and which means there is a performance degradation. So from the left hand of this figure, you can see that there is in many cases, the performance degradation happens. So specifically in the high-speed scenario, so we can see that the aggregation is not always efficient. So we already have existing work, which is designed by Chris, called the opportunistic retransmission and the penalization solution. And this solution, which is try to re-inject unacknowledged data from the slow path into the fast path. And afterwards, it halves the congestion window of the slow path. However, even with this method, we found that the performance degradation still exists. Because we found that this solution is only triggered when the performance has degraded. So this is a kind of reactive solution. And we found that this solution always try to aggregate all the paths, and this aggregation can be a problem by itself. Okay, this slide we try to use the math and to calculate the achievable aggregate throughput and to show when to select only the one path and when to select the aggregated path. So we can see from the right figure, and you can see that when the buffer is limited, so it's better to only use one best path. And when the buffer is large enough, and then we can use we can aggregate multiple paths. So hence, we think we need a new solution, and we require this solution. It should take proactive actions based on the path attributes. And also we require this solution can adaptively employ both the path or only the best path according to the path attributes. However, this proactive action sometimes can be counterproductive. So because we need to get the throughput of every single path and also the aggregated path. And these throughputs often estimated by the scene window as scene window by the RTT. We know that in a wireless environment, the scene window could be variant, and which is caused by the random packet losses. So the throughputs may be accurate. Okay, so we found BBR can help. The BBR is already part of the Mptcp since version 93, and we found that BBR can help to measure, to do the proactive measurement by offering the stable throughput and the stable RTT. And so BBR can help our measurement accurate. Hence, so that's why we consider to combine our solution with the BBR. But there is still a challenge that how to get the throughput of each pass and multiple paths efficiently. Currently, we have existing solutions. One is a modeling solution, but this modeling solution requires the path attributes such as the RTT, the PLR, and the bandwidth. this modeling solution is relevant to the specific congestion control and flow controls. So another solution is measurement. There is one direct method which can measure the throughput of each path and the multiple paths one by one. But this is time consuming. Another measurement is out-of-band measurement such as a PCP. This measurement is only measured once before the connection establishment. So we try to design our solution which can directly and simultaneously and periodically to measure the throughput of each path and the multiple path. And this modification only requires only require in the center. Okay, we call our solution PAD, which is the abbreviation of the proactive approach and to avoid the performance degradation. And this solution consists of two paths, throughput measurement and mode selection. For the throughput measurement, we employ two modes. One is the redundant mode, and the other is the MP mode. For the redundant mode, we use the redundant scheduler and to simultaneously to measure the throughput of each path and the best path. For the MP mode, we use the mean RTT scheduler and to measure the aggregated throughput. Of course, you can use all the schedulers as you like. After we measure the throughput, we compare the throughput and then we select the mode. The mode with the higher throughput will be selected. So if the redundant mode is selected, so we need to select the path with the higher throughput to send the data. And if the MP mode is selected, so we bond all the paths together to send the data. Okay. We also need to consider how to design for the two stages of the PAD solution. At the slow start stage, we only use the redundant mode. The reason is because at this stage, we know nothing about the path attributes. So, and also for each, after each RTT, and the scene window increases twice, and the scene window of each path increases isolated. So, which is due to the different RTT and different subflow connection set of time. That's why we use the redundant mode, which is try to make sure there is no performance degradation at this stage. And after we found that the path is fully utilized, so we've been to the congestion avoidance stage. At this stage, because we have to remember that the network is always time variant, so at this stage, we take turns to run the two modes and to measure the throughput of each path and the multiple paths. So after we measure the throughput, and then we compare and select the mode. Afterwards, we select the path. Okay, now let's see the results. In the left figure, the buffer is large enough. We can see that mean RTT scheduler performs good, and our PAD solution performs almost the same as the mean RTT. And actually, it achieves about more than 94% of the mean RTT scheduler. And in the right figure, the buffer is limited. So we can see that the mean RTT is not good. It only performs 26% of the best path, but our PAD solution can achieve almost the same as the best path. Okay, this slide shows a real scenario. We use the smartphone to download files from the cloud server, and we added delay into the Wi-Fi path, and we test 5 scenarios. And from the figure, we can see that for the scenario 1 and scenario 2 is a homogeneous scenario. So the mean RTT in the PAD performs good, and which benefits from the aggregated path. But for the scenario 3 to scenario 5, the RTT variance becomes larger, and mean RTT is not good. But PAD solution can achieve almost the same as a best path, which is the LT here. So that's it. I'm happy to take questions. So we are still keep working on improving this solution. So any interest?
Mia Kulevint. So when you use BBR, are you still coupling the congestion control somehow, or is it basic to independent congestion control, or like
It's uncoupled.
It's uncoupled. Okay. And why? Are you planning to couple that?
Because the BBR is a rate-based, so we do not need to, which is not window-based, so we do not need to cover with the two paths. And also, this measurement is independent on any other congestion control schemes or any other flow control schemes. So yeah, it's not relevant.
Okay. I mean, the goal of the coupling is that you basically always get at least as much performance as you would get on the better or on the best flow, right? And you're not using more resources than you would otherwise get. But this is like also a different discussion. And my second point is, did you see the presentations on BBR in the ICC-RG in the Internet Congestion Control Research Group?
Yes.
Okay. So you're aware of any problems there?
Thank you.
Anna Brunström. So there are also a number of other schedulers that have been proposed that tries to avoid the head of line blocking and the buffering problem. So it could also be interesting to try some of those, I think, for you.
Yeah, I would like to. So just try to say that our measurement is a direct measurement. So so if you use other the schedulers, so we can still use this measurement because we employ the schedulers and to help us to measure the throughput. Yeah. But we would like to try other schedulers.
Yes, because as I understood it, the problem you're trying to alleviate is related to the scheduling, right? And the asymmetry between the paths. So I think that with other schedulers that take that into account, you could reduce that effect.
Okay, thank you.
Any question?
Stuart Cheshire from Apple. I have one little comment about the presentation. You use, and this is something many people do, you use the word performance as meaning the same as throughput, as if the only performance we care about in networking is bulk transfer of large files. And there are other kinds of performance that matter. So on one of your slides, you said that using the path with the minimum RTT gives very poor performance. But if you want is very low latency, the minimum RTT is great performance. And one example of one of the things we use multipath TCP for at Apple is Siri, voice interaction. And we use it because we want very low latency. So in that case, the performance we care about is not the most throughput if that's a high delay link. We'd rather have the lowest delay link. So it's just a comment. Maybe use the word throughput rather than performance, because performance ought to mean many different things depending on the application.
Yeah, thank you. Yeah, here we only consider the throughput, the performance. Yeah.
And many people do. Whenever you hear marketing numbers about performance is better, they always mean throughput. And that's why I'm trying to clarify that I think we as an industry focus far too much on throughput as the only thing that matters.
Okay, thank you.
Zhen Cao from Huawei. So to your question, so I agree with you. We probably use the throughput is better for this draft. And for the question of MIRT, actually we use MIRT as the scheduling for the multipath aggregation. Right? So in the special case, MIRT is not only to decrease the latency of the application flow, but also in such cases of the discrepancy of two links, it also can help to increase the throughput when the two paths really, different from each other too much. Yeah.
So I hope it didn't sound like I was criticizing the work, because that was not my intent. I was just, I wanted to make the point, because it comes up a lot, that people very easily fall into the trap of thinking only about throughput. One of the reasons is because throughput is easy to measure. You run IPerf and see what number it says. And sometimes because it's easy to measure, and home users go to speedtest.net to see how fast their internet connection is. And only the really smart ones know that the round trip delay matters as well. So speaking for Apple, we don't care one bit about increasing throughput. We care about increasing reliability and decreasing delay. Because when you pull out the phone and talk to Siri and say, hey Siri, what's the weather? You don't need a gigabit per second to find the answer to that question, but you do want it to be completely reliable every time and fast.
But actually, last IETF, I think Apple has given presentation about the aggregation mode, although that's not open to all the developer right now. But that's something you are considering future.
Yes, that information is not secret. You know, Apple is very secretive, and there are things we don't talk about. But that was disclosed publicly at the Apple Developer Conference. The videos are online. Our engineer, Christoph Pasch, gave a description about how developers can use that. And we want to make multipath TCP available for our developers to experiment with, because they may think of things that we haven't thought of. And that's why we want all the capabilities available. For our own users right now, we have not really thought of a case where we care that much about more throughput. So I'm just saying, for our own use, we make that available, and if developers think of a way to use that, and I can imagine the Netflix client. If you saturate your Wi-Fi link and saturate your LTE link at the same time, then you get a slightly higher quality of 4K video on your iPhone by using, you know, both interfaces full blast. That might be something that other app developers think of creative uses for. I'm just saying that we at Apple are not planning to do that right now.
Anna Runström, I just wanted to add also that the min-RTT scheduler is not always giving you the best latency. Also, in asymmetry, it can also cause problems with the latency.
Okay, any more question? Okay.
Thank you.
Okay. Do we have a meet echo issue right now? Brad, can you hear me?
Yes, I can hear you.
Okay. So it's your turn.
All right. So hi, I'm Vlad, and I'm going to give you an update on our latest work on SOX version 6.
Oh, we cannot see you.
You cannot see me?
Yeah.
How about now?
Can you? Okay.
All right.
Oh, we cannot see your slide.
Me neither.
Oh, okay. Yeah, okay. Okay. And let's hold on a second. Okay. Okay, we are ready.
Okay, so I'm going to give you an update on our work on SOX version 6. So next slide, please.
Yep.
So I'm going to start by giving you a quick refresher. The main motivation as to why we're trying to bump the version number is that SOX 5 makes use of several round trips, and that's not really necessary. So we're trying to reduce the RTT overhead down to 0 in the optimal case. So next slide, please.
Yes.
So the basic idea behind SOX 6 is that the client is optimistic and sends as much information as possible up front. So it tries to authenticate itself, it makes a request, etc. And SOX is also extensible via options, so you can add all kinds of new functionality. And it also has support for TFO and zero RTT authentication. So next slide, please.
Yes.
So this is basically how SOX 6 looks when compared to SOX 5. So in SOX 5, the client first advertises its known authentication methods, and the server, the proxy, chooses one of those methods. And then they go through the authentication process. Then the client makes a request for the proxy to open up a socket, and only then can data flow. In SOX 6, the request contains the client-supported authentication methods. It also tells the proxy what server it should connect to, and it also sends a chunk of data. The proxy replies with an authentication reply, and then the authentication process can continue. And as soon as the client has authenticated, the proxy sends an operation reply. So next slide, please. And in case zero RTT authentication is supported, on the client's second attempt, it gets an operation reply in one RTT, and basically data starts flowing right away. Next slide, please. So in our latest work, we've been focusing on security. SOX 5 allowed for in-protocol encryption. We've decided to replicate that and just run SOX over TLS. Now, TLS 1.3 has support for early data. That means that on the client's second connection attempt and from then on, it can send data as part of its first packet. This incurs a zero RTT overhead, but it's prone to replay attacks. Now, since a SOX request also has zero RTT overhead and can likely fit in that early data, SOX is sadly also prone to replay attacks. So we needed some mechanism that makes our SOX requests idempotent. The next slide, please. So in order to do that, we've added some options that the clients can use to make the requests idempotent. So authenticated clients can be granted tokens that they afterwards spend on requests. So proxies actually allocate tokens on a per client basis. This whole negotiation takes part is part of SOX requests and operation replies. So the authentication replies have nothing to do with it. So next slide, please. So the client starts by requesting some tokens. Here we've got the three SOX control messages, like the request, the authentication reply, and the operation reply. So next slide, please.
Is this wrong one?
No, it's okay. I've been having feed issues. So the client can include a token request as part of the SOX request, in which basically says, please give me that many tokens. After it finishes authenticating, the proxy replies with a window advertisement, which basically tells it what tokens it can use. So next slide, please. So the token request just includes the requested window size. Basically says, please give me this many tokens. The client can use it as part of any request. If it doesn't have a socket if it doesn't want to open a socket right away, it can just use a no-op request, which basically does nothing. This is secure as long as it's not done over TLS early data. So client implementations should avoid using TLS early data when making token requests. Next slide, please. So the server, so the proxy replies with token window advertisement. Basically, it contains two integers, the window base and the window size. The window base is the first usable token. The window size is basically the number of tokens that the client can use. So, for example, the base is 10 and the size is 3. That means that the client can use the tokens number 10, 11, and 12. So next slide, please. So once a client has some tokens to spend, it can start spending them on requests. So the client should include a token expenditure option as part of its request. And the server basically sends back an expenditure reply as part of the operation reply, and an optional window advertisement in case the window has changed. So next slide, please. So the token expenditure is straightforward. It just contains the token that the client is trying to spend. Clients should tend to spend their tokens in order. So next slide, please.
You are not seeing the slide?
I can see it now.
Okay.
So the token expenditure reply includes a response code. If the token was out of window, or if the proxy had already seen the token, then the token is basically rejected and the operation fails. The next slide, please. Proxies can unilaterally increment the window base. That basically happens whenever so clients don't have to put in window requests in order to get more tokens. So if, for example, the client has spent its first 10 tokens, the proxy is free to shift the window 10 positions to the left. Also, if the client ends up spending higher tokens, the proxy can decide to shift the window past the gaps it has left in the token space, as to not create any problems and generate new usable tokens for the client. So next slide, please. So we're gonna focus more on Mptcp for our next draft. We're thinking about including options that via which the client can request that the proxy use a certain path manager or a packet scheduler for Mptcp. And we're also thinking about adding better reverse proxy support. SOX 5 only lets you accept one connection from the outside, and then if you want to accept another remote incoming connection from a remote location, you have to make another request. So we're thinking about adding some functionality via which the client can listen on a socket and then tell the proxy to forward incoming connections to that socket. So next slide, please. So there's another draft by Olivier that deals with a similar issue. What our two proposals have in common is that there's no controlled data aside from the initial exchange. So afterward, data flows verbatim via the proxy. However, we have chosen different starting points. So SOX 6 is purely a layer 5 protocol. It can be run over basically any reliable byte stream. So it can also be run over TLS. And while TFO is highly beneficial to SOX 6, it's not required. And in fact, as long as TCP works, SOX works. And that's about it. I'll be happy to take questions.
Any questions? So Brad, one question.
Yes.
Can you hear me?
Yes.
Your token stuff you mentioned, it's new stuff. It's a new feature for the SOX basic stuff, because you have in the last presentation you haven't mentioned that, in my understanding.
Yes, it was added in version 01 of the draft.
Okay. And this token is designed to maintain idempotency
Yes.
or any other purposes? Just for me?
No, it's just for idempotence. So if you're using TFO and the SYNAC is lost, you're not at risk of doing the same request twice. Or if some attacker is doing a replay attack, it can't.
Right. So then when we don't have to worry about the idempotency, then we don't have to use token?
Yes, that's entirely optional.
Okay. Any other questions? Okay. So if there is no more questions, thank you so much for Brad.
Thank you.
Yeah. You want to say something at the end? Okay.
No last word for me.
Okay.
Bye-bye.
Thanks so much.
See you.
Bye. See you. Okay. So since now we consumed all the agenda today, so you want to add anything? End of the meeting? Okay. So we still have a time, but let's enjoy some times before go to social meeting, and see you in London. Thanks for joining the session. Thanks so much. Okay. Do you have Blue seat? I think we have one more Blue seat.